Welcome to my video about magnetic field creation. There are three ways to create a magnetic field. One, through a permanent magnet. We won't really talk about that in this video. Secondly, through a current carrying wire, which we will talk about, and also with solenoids. Current carrying wires and solenoids both require electricity to create the field. So first let's talk about current carrying wires. This is just a simple wire with a current flowing in one direction, such as this one drawn here. The current is going in one direction, and because of that flow of current, there is a magnetic field that is created in the direction that is clockwise if you are looking in the same direction as the current. It's also counterclockwise if you're looking the opposite direction. We know that because we have a mnemonic that we use, that you can use, that is, clocks have X's on their faces. When you draw something that is going into the page, for example, this wire, if it were turned, it would have an X. And this wire, we know because of the right-hand rule, would have a magnetic field going in the clockwise direction. So that's where we get the clocks, clockwise, have X's on their faces. So you're facing in the direction that you would see the X. So now that we know the direction of the magnetic field, or the B field, now we may want to know how strong it is, or how well it can affect something that enters the magnetic field. So quantitatively, we have this equation, B being the B field, or the magnetic field, is equal to this constant over 2 pi. That's just, none of these are variables, so none of these change. Multiplied by the current that is running through the wire, divided by the radius from the wire the particle is. So if a particle is this far out, the radius from the center of the wire, so if this is a wire, the center would be here, not at the surface. So the radius is from the center of the wire to the particle. And that's what's given here. And you can see that as the radius gets larger, this expression gets smaller. So the field likewise gets smaller. And as the current goes up, the magnetic field also goes up. You can see that here. So now that we're done talking about current carrying wires, we can move on to solenoids. Solenoids are purposely designed to create a constant magnetic field within the solenoid, similar to in electrostatics when we have parallel plates. They're not things that appear in nature, but they're things that are manufactured for the specific purpose of having these constant magnetic fields. A solenoid looks somewhat like this. Physically, it's somewhat like this. I have a wire that is coiled up, and this, both ends of the wire would go to some sort of battery or power source, and that would cause a current to flow through this wire around and around. And that current that's going through the wire, if it's going this way, will, if you use the clocks that have X's on their faces, you see that it's going that way, so it has a clockwise magnetic field. And so you see that inside the solenoid, it has a field going in this direction. So, and each of the turns of the wire create more and more of that field that goes through the solenoid and then out as well on all sides. If you want to figure out, like I just did, you can use the same mnemonic that we use for the current carrying wires, and think about each turn of wire, and think about how each turn of wire is creating a field, and in what direction that field is pointed. So if you have this solenoid, the current is going this direction. You'll see that the current all the way around is producing a field that that is in this direction. So now, again, that we know the direction, we may want to figure out how to analyze a solenoid problem quantitatively. So we have this equation, B, again, is the magnetic field, is equal to this constant multiplied by N over L, which is the turn density. So the number of turns, so in this case right here, 1, 2, 3, 4 turns, and in this, this would be the length that the 4 turns are in. So if this length were 4 centimeters, then the, 0.04 meters, then the turn density would be 0.01 per meter. So, and then you multiply that figure by the current flowing through the wire, and then you get the magnitude of the B field within the figure, the solenoid. In this equation does not give you the B field of anything outside of the solenoid. It only gives you this constant B field that's within the solenoid. And that's the main purpose of a solenoid. So that's all you really need for a solenoid problem. So let's look at this sample problem. What is the field strength and direction of the center of the solenoid? This is the solenoid. Let's look at this qualitatively first. This solenoid has 5 turns of wire in a 0.01 meter length. Things that we're going to need. We know that we're we're going to need to figure out the direction. So let's do that first. The direction of the field is related to the direction of the current, right? As we found out earlier. So since the battery is facing this way, hooked up this way, the current will be going in this direction, right? So it'll go through the turns thusly. And if you think about this point on the solenoid, you can think about the current as going into the page, in which case the field would be clockwise, because clocks have X's on their faces. So we already know that the field direction is going to be going left on the paper. So we've already got that out of the way. Now for the field strength. This is where we're going to need to use the equation. If you remember, B is equal to the constant times N over the length, that's the turn density, times I. What are things we know? We know that we know the turn density because we know that there are 5 turns of wire over this distance. So if we want to go ahead and plug that in, we're left with the current. Initially it looks kind of hard to figure out the current, but if you know anything about circuits, you will hopefully realize that this fact, V equals IR, that's the voltage, and then the current and the resistance. So we know the voltage through the circuit is 9 volts. And we know that the resistance, there's only one resistor in the circuit, so it's 3 ohms, and that leaves I. And if you solve for I, you get 3 amps. And that you can plug straight into here. So now at this point, all you can do is plug this into your calculator, and there's nothing really that you can do wrong except for punching in buttons. And if you get the right answer, you will come out with 0.00188 Tesla. And as you can see, this is really not that much when it comes to the strength of the field through the solenoid. So that's all I have. Thank you for watching, and